The first module we'll be building is the clock module. And like every computer, it needs a clock signal to tell the controls to move from instruction to instruction. And in modern computers, we'll have a crystal oscillator, something like this or like this. And we will not be using this on our build because they are just too fast. This one is a 50 megahertz and this one a 10 megahertz oscillator, and we don't want that. We want a much slower clock pulse, so we'll be able to see what's going on. So we need a million times slower than this one. So we don't need a megahertz, we need just the hertz. So we're building the clock generator from a simple RC circuit, a capacitor and a resistor that will be charged and discharged. And the time constant will be measured to get a square wave output from it. And luckily for us, the LM555 timer IC will do this for us. Just with an external capacitor and resistor, it will control the charge and discharge of these components, and we'll be able to create a clock pulse from it, adjustable clock pulse. Also, with this same IC, we can use it to make a debouncer in order to get our manual clock pulses, to advance the clock manually and debug some program or just go even slower than the clock can. And also a debouncer for the manual automatic clock switch. So we'll just go through the schematics for the clock module a bit. And as I said, the clock module is based on the LM555 timer IC. And the first one is configured as an S-stable clock, which means it's not stable in any of the edges. It will oscillate between high and low, and that's exactly what we want. And in short, it does this by charging and discharging this capacitor here, C1, 1 microfarad capacitor, through this resistor network, this R1, R2 and the variable resistor. It's a potentiometer. And the internal circuitry of the 555 timer, what it does is it has two comparators from 1/3 and 2/3 of the voltage it is applied to, and it keeps charging and discharging the capacitor between these two boundaries, 1/3 and 2/3 of the voltage. So by changing either the capacitance or the resistance, we change the time constant and thus change the frequency it will oscillate. And that's exactly what we want to do. So the automatic clock generator is this first part of the schematic here. The second part of the schematic is also based on the 555 timer, but it's only used as a monostable operation, which means it is like a one-shot trigger. It also is also based on our C network on charging and discharging this capacitor here through this resistor here. And it's necessary because if you only use the push button as a manual clock, we won't have the result we want, because manual switches are not perfect. When we push the switch, it won't close the contact perfectly. It will generate a lot of noise, and we want to avoid this. So we use this timer to get rid of this noise. So as soon as the first contact is made on the switch, the timer starts to charge this capacitor, and the output is held high. And when the output reaches the threshold of 2/3 of the voltage, then the capacitor is discharged again and the output goes low. And I've calculated this time constant to be around 1/3 of a second. So it's more than enough to get rid of any noise created by the switch. And the last one, the last module here from our clock is based also on the 555 timer, but we're this time not using any time constants. We're just using it as a flip-flop. We are accessing the internal RS flip-flop by using the reset pin of the 555 timer that we can connect either to 5 volts or to ground through a switch, and the comparator on pin 2 that we can also connect to 5 volts or to ground. And then it will also filter out any bounces of this switch, because it will just set or reset this internal flip-flop. And in the end, we must mix these 3 signals together to get one clock out only. And we'll do this by a little of combinational logic using a 74 HCT00 NAND gates, 4 NAND gates, and also a 74 HCT04, the hex inverter. So that's it. Let's start building it. So after a few hours of soldering, that's what we got. And we have here floating around our halt signal wire, which will be after connected to the control logic. And this input power jack that is just not permanently connected, just for testing. I have arranged the components in a way to sort of to emulate a breadboard, so it would be easier to lay out the components. It could surely be done in less space, but I chose to make it like that to be easier to build and debug. Okay, there we have it. A clock is pulsing away, and we can halt it and manually pulse it. Great. So just for fun, we can measure the output of these timers in the oscilloscope to take a look at the output waveforms. And if we measure pin 2 of this first timer, with the trigger, which is also connected with the threshold to the capacitor, we will see the curves of the capacitor charging and discharging. And that's it. And as we can see, the maximum voltage it achieves is 3.9 volts and minimum 1.96, which is more or less 1/3 and 2/3 of the voltage. And if we measure the output, then we can see the square waveform of the clock pulse.